Welcome to Future Vision Talks. Today, we are peering into one of the most significant technological shifts on the horizon, a paradigm shift that promises to redefine the boundaries of computation, and in doing so, threatens to dismantle the very foundations of our digital security. We are talking about the immense power of quantum computers. Right now, as we speak, a silent digital harvest is underway. Nation-states and sophisticated individual actors are intercepting and storing vast rivers of encrypted data. This includes everything from passwords and bank details to sensitive corporate intellectual property and state secrets. But here's the curious part. They can't open these files. The encryption, for now, is too strong. So, why are they doing it? The strategy is known in intelligence circles as store now, decrypt later. It operates on a chillingly simple premise. They believe that within the next decade or two, they will have access to a machine of unprecedented power, a sufficiently large quantum computer that can break this encryption in minutes, not millennia. The information they are collecting today, industrial research, pharmaceutical formulas, government intelligence, will still be immensely valuable in 10 years' time. This isn't a theoretical threat. It is an active, ongoing operation, and everyone in the world of cybersecurity is aware of it. The U.S. National Security Agency has been unequivocal in its assessment, stating that a cryptographically relevant quantum computer, if built, would be capable of undermining all widely deployed public key algorithms. The clock is ticking. Even though these powerful quantum machines are still years away from full realization, their shadow is already stretching across our present, forcing a global reckoning. This is precisely why the U.S. Congress has passed legislation mandating all federal agencies to begin an immediate transition to new, quantum-resistant methods of cryptography. The race is on to build digital fortresses that can withstand an assault from a technology that doesn't yet fully exist. To truly appreciate the magnitude of this shift, we must first understand the system it seeks to overthrow. Our current digital world is built upon an encryption framework that has been remarkably successful, working effectively for over 4 decades. But its roots go back even further. Up until the 1970s, if you wanted to exchange private information with someone, say a military general and a field commander, you first had to meet in person to share a secret key. This same key would be used by both parties to scramble and then unscramble the messages. This is known as symmetric key cryptography. Its security is absolute, but only as long as the key remains a secret shared solely between the intended parties. The fundamental and seemingly insurmountable problem was, how do you share that secret key with someone you've never met across an unsecured channel like a telephone line or the mail without it being intercepted? This cryptographic conundrum was solved in 1977 by 3 brilliant scientists, Rivest, Shamir, and Adelman. Their breakthrough, known today by their initials RSA, was a masterpiece of mathematical ingenuity. It introduced the world to asymmetric key cryptography. Here's how it works in its elegant simplicity. Imagine every person has 2 uniquely large prime numbers, which they keep utterly secret. These are their private keys. They then multiply these 2 primes together to create an even larger number, which they make public for everyone to see. This is their public key. Now, if I want to send you a private message, I use your big public number to garble my message. I scramble it using a mathematical function that is a one-way street. It's computationally easy to perform the encryption, but it is designed to be impossibly difficult to reverse without knowing the original 2 prime factors. So while it's easy for you, the intended recipient, who holds the secret primes, to decode the message, it is effectively impossible for anyone else. The only way for an eavesdropper to break the encryption is to factor that enormous public number back into its 2 prime components. Now, someone could certainly try to factor it using the world's most powerful supercomputers. The best-known classical algorithm for this task is called the general number field sieve, but modern cryptography uses prime numbers that are astronomically large, typically around 300 digits long or more. To put this into perspective, factoring the product of 2 such primes,
even with a supercomputer harnessing the combined power of thousands of the fastest processors, would take not years, not centuries, but on the order of billions of years, far longer than the current age of the universe. The security of our digital lives rests on this seemingly unbridgeable computational chasm. But then enters the quantum computer, a machine that operates on an entirely different set of rules, the counterintuitive and fascinating laws of quantum mechanics. To understand its power, we must first grasp the fundamental unit of classical computation, the bit. A classical bit is a binary entity. It can be in one state at a time, either a 0 or a 1. If you have 2 bits, they can be in one of 4 possible states, 00, 01, 10, or 11. Let's say each of these states represents a number, 0, 1, 2, or 3. If we want to perform a calculation, for instance raising the number 7 to the power of the number represented by the bits, we can only do it for one state at a time. If the bits are in the state 10, representing 2, we calculate 7 squared and get 49. The other 3 states and their corresponding calculations remain unperformed.
A quantum computer, however, uses quantum bits, or qubits. Like a classical bit, a qubit has 2 basis states, which we also label 0 and 1. But here is the first quantum revolution. Unlike a classical bit, a qubit does not have to be in just one state at a time. Thanks to a property known as superposition, it can exist in a complex combination of both 0 and 1 simultaneously. It's as if the qubit is spinning in multiple directions at once. This means that a single qubit can hold a spectrum of possibilities between 0 and 1 at the same time. When you have 2 qubits, the power scales dramatically. Because of superposition, the 2 qubits can exist in the simultaneous combination of all 4 possible states, 00, 01, 10, and 11. Now, when we perform our calculation of 7 to the power of the number represented by the qubits, the quantum computer performs the operation on all 4 states at the same time. The result is a new superposition state containing all 4 answers. 7 to the power of 0 equals 1, 7 to the power of 1 equals 7, 7 to the power of 2 equals 49, and 7 to the power of 3 equals 343. This is quantum parallelism in action. The scaling is exponential. Add a third qubit, and you can represent 2 to the power of 3 or 8 states simultaneously. With just 20 qubits, you can represent over 1 million different states, performing over 1 million calculations in parallel. With 300 qubits, the number of states you can represent surpasses 2 to the power of 300, which is a number greater than the total count of atoms in the entire observable universe. This is the source of the quantum computer's seemingly mythical power. However, there is a profound and critical catch. All of these parallel answers are embedded within a fragile superposition. You cannot simply read out this superposition to get a list of all the answers. When you make a measurement on a quantum system, the superposition collapses. You get a single random value from among the possibilities, and all the other information is irrevocably lost. It would be like trying to read a book by exploding it. You might get a single random word, but the rest of the story is destroyed.
Therefore, the true art and immense challenge of quantum computing is not just creating superpositions to perform parallel computations, but in designing algorithms that can cleverly manipulate these superpositions. The goal is to amplify the probability of measuring the one answer you actually want, while causing the probabilities of all the wrong answers to destructively interfere with each other, effectively vanishing. This is an incredibly difficult task, which is why, for the vast majority of computational problems, quantum computers offer no advantage and are effectively useless. But as luck, or perhaps a deep connection in the fabric of mathematics, would have it, the few problems where we can design such clever algorithms
happen to be precisely the problems that form the bedrock of nearly all modern public key cryptography. The most famous of these is the integer factorization problem that secures RSA. In 1994, mathematician Peter Shor devised a quantum algorithm that could factor large integers exponentially faster than any known classical algorithm. Shor's algorithm is the sword of Damocles hanging over our current cryptographic infrastructure. To understand how it works, we need to delve into the beautiful and intricate dance of number theory and quantum interference. The core of Shor's algorithm relies on a mathematical fact that feels almost like magic. Let's return to our example of factoring a number n, which is the product of two primes, p and q. For a simple illustration, let's set n equal to 77. Now pick a number g that is smaller than n and doesn't share any factors with it. Let's pick g equals 8. If you start multiplying g by itself repeatedly, calculating g to the 1, g to the 2, g to the 3, and so on, and then look at the remainder when you divide each result by n, you will find that the sequence of remainders is periodic. It cycles. Most importantly, you will always, eventually, find that for some exponent r, g to the r divided by n leaves a remainder of exactly 1. In our case, 8 to the 10th is 1,073,741,824, and 1,073,741,824 divided by 77 gives a remainder of 1. So, 8 to the 10th is 1 more than a multiple of 77. We can write this as 8 to the 10th is congruent 1 modulo 77.
This exponent r is called the order or period. How does this help us factor n? We rearrange the equation. If 8 to the 10th is congruent to 1 mod 77, then 8 to the 10th minus 1 is congruent to 0 mod 77, meaning 8 to the 10th minus 1 is a multiple of 77. We can factor this expression as a difference of squares. 8 to the 5th minus 1 times 8 to the 5th plus 1 is a multiple of 77. Since 77 is a factor of this product, its prime factors, 7 and 11, must be hidden within these two terms. They are distributed between 8 to the 5th minus 1 equals 32,767 and 8 to the 5th plus 1 equals 32,769. They probably share factors with 77. To find them, we use a beautifully efficient 2,300-year-old algorithm from Euclid. To find the greatest common divisor, GCD, of two numbers, you repeatedly divide the larger by the smaller and replace the larger with the remainder until you get 0. The last non-zero remainder is the GCD. Let's find the GCD of 32,767 and 77. 77 goes into 32,767 a certain number of times, but we care about the remainder. 32,767 divided by 77 equals 425 with a remainder of 42? Let's calculate precisely. 77 times 425 equals 32,725. 32,767 minus 32,725 equals 42. So, GCD of 32,767 and 77 becomes GCD of 77, 42. 77 divided by 42 equals 1 with a remainder of 35. So, GCD of 42, 35. 42 divided by 35 equals 1 with a remainder of 7. So, GCD of 35, 7. 35 divided by 7 equals 5 with a remainder of 0. Bingo! The GCD is 7. We have found one prime factor of 77. The other is simply 77 divided by 7 equals 11. So, the recipe for factoring n is 1. Make a random guess, g. 2. Find the period, r, the smallest number such that g to the r is congruent to 1 mod n. 3. Use r to create two new numbers, g to the r by 2 minus 1 and g to the r by 2 plus 1. 4. Use Euclid's algorithm to find the GCD of these numbers with n, which will very likely yield the prime factors p and q. On a classical computer, step 2, finding the period r, is agonizingly slow. It's essentially as hard as trying every possible exponent, which for a 300-digit n is an intractable task. This is where the quantum computer unleashes its power. Shor's genius was in using quantum parallelism and interference to find the period r with breathtaking speed.
Here is how the quantum computer accomplishes this. First, we initialize two quantum registers. The first register is prepared in a massive superposition of all possible integers from 0 up to some very large value. The second register starts in the state 0. Through a series of quantum gates, we entangle the two registers. We compute the function f of x equals g times x mod n for every value of x in the superposition of the first register and store the result in the second register. The magic of quantum mechanics means this calculation is performed for all possible x values in a single coherent step. We are now left with an entangled superposition of all x f of x pairs. Now, if we were to measure the entire system, we'd get a random pair and learn nothing. But instead, we perform the key trick. We measure only the second register. Suppose we measure it and get a specific remainder, let's say 15, from our n equals 77, g equals 8 example. This measurement collapses the second register, but it also projects the first register into a very specific state. Because the function is periodic, the value 15 doesn't come from just one x. It comes from x equals 4, 14, 24, 34, and so on. All these x values are separated by the period r we are looking for. We now have a periodic superposition in the first register. This is where the second act of quantum magic comes in, the quantum Fourier transform, QFT. The QFT is the quantum analog of the classical Fourier transform, a mathematical tool that identifies the frequencies in a signal. If you apply a Fourier transform to a periodic wave, it will spike sharply at the wave's fundamental frequency. The quantum Fourier transform does the same thing, but for a quantum state. When we apply the QFT to our periodic superposition of states, 4, 14, 24, 34, and so on, it transforms this state into one that is highly concentrated around values related to the frequency, which is 1 over r. A final measurement of the first register will now, with high probability, yield a value from which we can directly deduce the period r. Once we have r, the rest is classical, easy arithmetic. We check if r is even, compute g to the r over 2 minus 1 and g to the r over 2 plus 1, and run Euclid's algorithm to find the factors. The quantum computer has reduced a problem that would take billions of years to one that could be solved in minutes or hours. The critical question then becomes, when will we have a quantum computer powerful enough to run Shor's algorithm on real-world cryptographic keys? It's not just about the number of qubits, it's about their quality. Early estimates suggested a need for 1 billion physical qubits to provide enough error correction to create a stable logical qubit. But progress has been staggering. By 2019, thanks to algorithmic and hardware improvements, that estimate had plummeted to around 20 million physical qubits. Today, the most advanced quantum processors have a few hundred to a few thousand qubits. While we are still far from the millions needed, the trajectory of progress appears exponential. The collision between required and available qubits is not a matter of if, but when.
This looming threat is the driving force behind one of the most important global scientific efforts of our time, the development of post-quantum cryptography. cryptographers have not been idle. They have been working for years to build new cryptographic systems based on mathematical problems that are believed to be hard for both classical and quantum computers to solve. In 2016, the U.S. National Institute of Standards and Technology, NIST, launched a global competition to standardize these new algorithms. After multiple rounds of intense scrutiny, where the global cryptographic community attempted to break the proposed schemes, NIST selected a handful of winners in 2022. The most promising family of these new algorithms is based on the mathematics of lattices. A lattice, in this context, is a regular grid-like array of points in a high-dimensional space. In 2 dimensions, you can think of it as an infinite set of points generated by taking all integer combinations of 2 basis vectors. For example, if your basis vectors point to 2, 1 and 1, 2, you can get to any point like 3 times 2, 1 plus -1 times 1, 2 equals 5, 1. The collection of all such points forms your lattice. Now, consider a hard problem called the closest vector problem. I show you a lattice defined by a particularly nasty, skewed set of basis vectors, and I give you a random target point that is close to, but not exactly on, a lattice point. Your task is to find the actual lattice point that is closest to my target. In 2 or 3 dimensions, this is visually intuitive and computationally easy. But as we increase the number of dimensions, the problem becomes astronomically difficult. In a proposed encryption scheme using 1,000 dimensions, every time you try to move closer to the target in 1 dimension, you might be moving catastrophically further away in the other 999. The number of possible lattice points to check grows exponentially with the number of dimensions, making it infeasible for any computer, classical or quantum, to solve. This hardness forms the basis for lattice-based cryptography. Here's a simplified view of how it works for encryption. Your public key is a description of a lattice using a bad, hard-to-work-with basis. Your private key is a good, short set of basis vectors that makes it easy to solve the closest vector problem for that specific lattice. If I want to send you a secret message, I first encode it as a lattice point. Then I add a small, random amount of noise to it, shifting it slightly off the lattice. I send you this noisy, off-lattice point. For an attacker who only has the bad public basis, finding the original lattice point is virtually impossible. But you, with your private good basis, can easily snap the noisy point back to the correct lattice point, thereby decoding the message. Your secret remains safe.
This is just one of the brilliant mathematical shields being forged in labs and universities around the world. Behind the scenes, an army of researchers, mathematicians, and cryptographers are the unsung heroes working to ensure our digital future remains secure, protecting our privacy, our critical infrastructure, and our way of life from the very real threat posed by the incredible power of quantum computation. The story of quantum computing is a profound reminder that technological progress is a double-edged sword. It offers solutions to problems we once thought were unsolvable, from designing new materials to modeling complex climate systems. But it also forces us to constantly evolve, to anticipate future threats, and to rebuild the foundations of our society. At Future Vision Talks, we believe that understanding these seismic shifts is the first step toward navigating them successfully. The quantum future is not a distant abstraction. It is taking shape today, and its implications will resonate for generations to come. Thank you for joining us on this exploration.